The engine exhaust system of the B-21 Raider is one of the most critical components in preserving the aircraft's low observability and survivability in heavily defended airspace. As part of the U.S. Air Force's next-generation long-range strike bomber, the Raider is designed to operate in environments where legacy bombers would face significant risks. The exhaust configuration, along with its placement and structural integration, plays a decisive role in minimizing the aircraft's thermal signature, reducing detectability by infrared-guided weapons and surveillance systems, and supporting its broader stealth mission set. Unlike conventional aircraft that prioritize engine thrust efficiency or high-speed performance through exposed, circular afterburning nozzles, stealth bombers like the B-21 are designed for strategic penetration. This means getting close to highly defended targets, such as hardened infrastructure or mobile missile platforms, while avoiding early detection or tracking. In this role, a high infrared signature is a major vulnerability. Heat-seeking missiles, airborne IR sensors, and ground-based infrared search and track (IRST) systems can locate an aircraft based purely on the temperature difference between the jet exhaust and the surrounding atmosphere. The hotter and more concentrated the exhaust plume, the easier it is to detect. To counter this threat, the B-21 appears to adopt a recessed, narrow slot exhaust system. The layout is embedded into the upper rear section of the fuselage, blended smoothly into the trailing edge of the aircraft. This design minimizes the exposure of hot engine components and provides substantial shielding from both below and behind. The top side positioning of the exhaust outlets also leverages the airframe itself as a thermal barrier. Any observer or sensor located at a lower altitude would have a limited line of sight to the hottest parts of the aircraft. In addition, the B-21 likely employs an internal cooling and exhaust mixing system. This involves taking cooler bypass air that flows around rather than through the engine core, and combining it with the hot exhaust gases inside the aircraft before expelling them. This technique dilutes the temperature of the final plume, lowering its infrared signature. Such a system would also benefit from modern temperature-resistant materials and coatings that reduce the emission of residual heat from surfaces near the exhaust. These materials would have advanced significantly since the B-2's design was finalized decades ago, allowing the B-21 to accomplish the same or better stealth performance with potentially simpler or more compact geometry. The geometry of the exhaust exit itself shows an evolution from the B-2's more complex multi-surface nozzle area. On the B-2, the trailing edge includes a serrated or sawtooth pattern behind the exhaust. This detail was likely implemented to scatter radar waves and further diffuse heat emissions. On the B-21, early imagery suggests a cleaner, straighter edge. This might seem like a downgrade at first glance, but in reality, it's likely the result of advancements in materials engineering, structural shaping, and computer-optimized airflow design. A straight edge doesn't necessarily mean a higher signature, it may instead point to a better overall integration of stealth features that achieves the same or improved effect with fewer moving parts or less maintenance. Another likely improvement in the B-21's design is how it handles heat buildup over time. On earlier stealth aircraft, such as the B-2 and F-117, repeated thermal cycling of the exhaust system, caused by takeoffs, landings, long-range missions, and altitude transitions, could lead to heat-related fatigue, material warping, or signature degradation. The B-21, designed from the ground up with decades of operational feedback, almost certainly includes better thermal expansion management, possibly using ceramic-based insulation or next-generation metal alloys that maintain structural integrity and signature performance over time. Because the B-21 is expected to be more maintainable and more sustainable than the B-2, the exhaust system is also likely designed with production and life cycle costs in mind. One of the lessons from earlier stealth programs was that extreme precision and complexity in low observable features can result in extremely high maintenance overhead. For example, the B-2's trailing edge and engine masking required constant upkeep to ensure the stealth coating remained intact, especially around the hottest surfaces. The B-21 likely mitigates this by simplifying the structure where possible, incorporating modular panels, and using materials that are more resilient to temperature and environmental wear without constant repair. Additionally, the B-21's exhaust design supports its modular, digital-first development process. The Raider is built using open architecture systems, which allow for faster integration of upgrades and new technologies. That design philosophy likely extends to its propulsion system. If future threats evolve in ways that demand greater thermal masking or alternative cooling strategies, the B-21's modular design would allow updates to the exhaust system, whether through revised nozzle shaping, different coatings, or advanced thermal dispersal technology, without having to redesign the entire aircraft. Another important consideration is radar cross-section (RCS) management. While infrared signature is a major concern for the exhaust area, the geometry must also prevent radar energy from being reflected directly back to emitters. The narrow, flush-mounted exhaust outlet likely has internal shaping that deflects radar waves away from the source, and its alignment with the airframe's contours reduces the chance of creating radar hot spots. Even the temperature difference between hot engine gases and cold ambient air can sometimes create a small radar signature, so careful control of that transition is critical. The radar's exhaust system therefore supports the aircraft's primary goal, to remain undetected while approaching, striking, and exiting hostile environments. That includes being nearly invisible to radar, difficult to detect in the infrared spectrum, and resistant to long-range tracking. By shaping and cooling its exhaust output, the B-21 can avoid triggering early warning systems that would otherwise cue missile batteries or alert airborne patrols. Everything about the B-21 exhaust design aligns with the aircraft's strategic mission profile. It is not built for speed, maneuverability, or short-range tactics. It is built to project power over intercontinental distances, penetrate air defense networks, and carry out precision strikes without warning. Its stealth relies not just on its shape or materials, but on a whole system approach that includes heat signature reduction, radar deflection, acoustic masking, and electronic warfare capabilities. The exhaust system of the B-21 Raider is a key element in its stealth architecture. It is the product of decades of American research, combat experience, and technological innovation. The design achieves a balance between performance, low observability, and long-term sustainability. While many details remain classified for operational security reasons, the exhaust system reflects a deliberate and focused strategy to keep the Raider survivable, undetected, and lethal in the most challenging air defense environments the U.S. may face in the future.